All right. Hey guys, what's up? Welcome to day 4. Our last formal day. Congratulations for those who made it this far. You know how these things go. 500 people apply, 200 show up to the first lecture, then it's half and half. So I guess now we're left with like the subset of people who are like actually interested in the course and put in the hard work. And I'm sure people are watching the recording as well. So yeah, great job. Today's going to be day 4 about our first quantum algorithm, the first one that's usually taught, Deutsch's algorithm. So if you recall on day 1, I said Deutsch's is great in the sense where it shows that okay, it's an algorithm that displays that okay, a quantum computer can do something like better than a classical computer can. But again, it's not a really useful problem. So, but later on, hopefully, we can see some more useful problems when you go on to learn QC formally. Okay, so Minh, I guess you can take it from here.
Yep. Thank you for the introduction, Adam. As he said, for those who are left today, you guys are in for a treat because Deutsch algorithm, like even though it's not like useful stuff, it's still like super cool because like so many algorithms comes from here, like Shor's algorithm, Grover's algorithm. They start from Deutsch. So let's start it out, guys. So okay, so let's recall from yesterday, right? Oh, also guys, you might want to get out your pens and papers for today because I'll be writing down a lot of stuff. So from yesterday, right, we did super dense coding. We did teleportation. And we did BB84. And this was covered by Emilio yesterday, right? And so collectively, these are what we would call communication protocols. Right, and their function is to transport information using quantum phenomena, right? And if you guys remember, we have 2 quantum phenomena that we are using, right? There are 2 quantum phenomena. The first one is superposition. And this is just a fancy term in physics for linear combinations for those who have taken linear algebra. And this is when you have a weighted sum of the basis vector of a vector space, right? So for example, like a principal example would be h applied on 0 would be equals to 1 over square root of 2, right? Of 0 plus 1. That's one example. And also the Hadamard gate applied on the state 1 would be equals to 1 square root of 2 of 0 minus 1. And this should be revision for you guys, right? But this is an example of superposition because we did have a weighted sum of the 0th ket and the 1th ket. So, and the other quantum phenomena that we are using is entanglement, right? So let me just recap what entanglement is for you guys. So let's say this is one example of an entangled circuit, right? So we have a 0 ket at the input, and we have a Hadamard gate here, and then we have a CX gate here, and that's the output, right? So I think this is also in your homework for, I think it was day 2. So let's say you have one checkpoint here. This is checkpoint 1, right? And this is checkpoint 2 and checkpoint 3, right? So at 1, you have just have 0, 0, right? And also, guys, in this lecture, I will be using this notation. For example, say A, B, and this is equals to A tensor B. And here the tensors imply, the reason I removed it is for conciseness, right? Like I don't want to write so much. I'm lazy, you know? So, and at 2, you have a tensor product of H and the identity, right? And that's applied on 0, 0. And this is equals to H of 0 tensor I of 0, right? And then if you write H in terms of the linear combination or superposition, you would get 1 over square root of 2 of 0 plus 1. And that is tensor by 0, right? So should put a tensor product here. But you can distribute a tensor product through sum, as said by Alejandro in lecture 1. So you have this case here. So I hope that this makes sense to everyone now. And at 3, which is this step, we applied a CX gate to the whole collection, right? And this would be equals to 1 over square root of 2 of CX 0, 0 plus 1, 0. And again, from lecture 1, you know that you can distribute a matrix multiplication through sum, right? So you get 1 over square root of 2 of 0, 0 plus 1, 1, right? And this is an entanglement state, right? So moving on from this, with this in mind, we can get into our first quantum algorithms, right? So quantum algorithm, actually, let me do it in red because it's big, guys. So what is a quantum algorithm? A quantum algorithm is an algorithm that provides speed up in computation, right? Using quantum phenomena. Right, so I want you guys to distinguish between quantum algorithms and quantum communication protocols, right? So the difference is that these things, superdense coding, teleportation, and BB84, they transport information, whereas quantum algorithm, they perform calculations or computations on different information, right? So let me define the term computation, right? So it takes value. So a computation is also called a calculation. So they perform some operations on information, right? That's like a super general definition of computation. And one of the simplest computation you could do with a computer, right? Because computer does computation, it's in the name. It's a function. And what a function is that it's something that takes value from something called an input space to an output space, right? So you guys might have seen this in your high school class. So you have X, right? That's an input, and you put it into a box, and that's, let's call that F, right? It's a function, and that gives out what? An output, and we call that F of X. This is just standard stuff, right? So let's create like an example of F of X, right? So we're working with binary here still. So let's say F of X is equals to, move that down here, 0 if X is even, and 1 if X is odd. Yeah. So let's say X is equals to, I don't know, 0, 0, 1, 1, 0, 1, right? And the way we read binary is from left to right, right? So this bit here would be the least significant bit, and that would determine whether our number X is even or odd, right? So in this case, because we have a 1 here, so obviously it is odd, right? So let's say we put X, right, which is 0, 0, 1, 1, 0, 1 into a function, right? And what do we get out? We get out 1 because it's odd, right? So easy stuff. So these things here are what we call classical function. And the reason I would like to make that distinction is because we are distinguishing it from something called a quantum function, right? A quantum function. It's also called an oracle, but so I'll get to that in a second. So a quantum function, and the reason I'm distinguishing it from classical function, actually, let me make this red because it's important. The reason I'm distinguishing it from classical function is because there are some constraints to it, right? Because you're working with a quantum systems, and quantum systems are like super weird. So you're always constrained to it, right? So first, a quantum function, first of all, has to be unitary. And that, I think it satisfies something like u to the -1 is equals to u dagger, right? So you have the situation, so u dagger, u equals u dagger equals I. So that's a definition of unitary, right? It is also reversible. So what this means is that, let's say you have an input space x here, right? And you have two different values, and you have an input space y here. You have two different values. You can map them to each other, but the mapping has to be unique, right? So what this means is that, let's say I give you a value of y, right? And that's equals to f of some a, right? But this would also implies in both directions that x is equals to a. So the mapping is unique. So this is also called a bijection. So the quantum function has to be bijective, right? And one more constraint is that the input size has to be equals to output size. Oops, no more space. Right, and this is super important because sometimes when I do my quantum stuff, I forget about this, and like it messed up so many things. So the input size has to be equal to output size. It has to be reversible and unitary. So these are the conditions for our quantum function, right? So the way we can implement a quantum function, let me write that as QF, is with an oracle, right? So today we are restricting ourselves to a 2-bit oracle. When I say 2-bit, I mean 2-qubit, because obviously we're working with quantum here and no one uses bits anymore. Qubit, right? Oracle. So this is what it would look like, right? Okay, so we have 1 qubit here. That's the first qubit. Let's call that the input bit. That's a qubit. That's a ket of x, right? And the bottom is called a target bit, right? And we call that ket of y. And now y here, it's not an output per se. It's more like an auxiliary bit that you use for computation, but it's not your input. It's just something extra you use that facilitates that computation, right? So you have these two things, the input bit and a target bit, x and y. You run them through an oracle, right? So this is called F in normal case, as we have seen here. But in quantum, since things are unitary, you do u sub f, which is just like a unitary that applies the function f here. Okay, so u of f, and what you get out on the top bit is x, and the bottom bit is y XOR f of x, right? And the reason for this should be cleared in a little second. So wait, so let me just tell you what this thing is. So this thing stands for XOR. And let's say, let me give you the truth table of XOR. Let's say I have A, B here, and A and B would be just some binary value, right? So 0, 1, 0, 1, and A XOR B would be equals to 0, 1, 1, 0. Right. So whenever you're working with XOR, you can just remember this truth table. It's not that long, or you can just look at this, no pain in that. So you have this truth table here. And the reason why we pass the input bit from here to here, and we did something like this to the output bit, is to make sure that our computation is reversible, right? Because if we just put X and Y x to f of x here, it's not going to be reversible, and it's going to be clear when I show you like an example, right? So any questions so far before I get into those examples? Adam, Emilio?
Anything in the chat? Okay. Can you please elaborate on input size equals output size?
Yeah, for sure. Okay, let's say, right, you have like just a circuit, right? Just a quantum circuit. It doesn't even have to be like an ORC or a function, because a function is applied on what? Like a circuit, right? So let's say you have a circuit, right? You have some input here, let's say A, B, C, right? So you're passing 3-bit in, you need to get 3-bit out, right? Like A, something like F of A, G of B, H of C, right? So how many ever bits you're passing into your circuit, you need to get out those bits, right? You need to get them out, because you got to do that because of some law of thermodynamics or something like that. Like I'm not really sure, but that's just one of the rules, you know. So is that clear for you? Yeah.
Yeah, thanks.
Anything else?
That seems to be it for now.
Okay, cool. So I think we were just talking about, what were we talking about? Okay, let's get into some examples of the kind of functions that we can implement with these 2-qubit oracle, right? And this is going to be super weird, and like I didn't even get it at first, right? So the kind of functions we can apply with this 2-qubit oracle here is something called you can apply a classical 1-bit function, right? And it's called a unary function, right? So in terms of the mathematics, you would map it from the space of 0 and 1, and you would map it to the space of 0 and 1. So it's just single bit input output, right? So let's say x is equal to 0 or 1 because it's single bit, right? Yep, let's say there's a function a, right, that takes an x, right? And let's say for any x that it puts in, it would always spit out 0, right? So 0, 0, right? So we would call this a constant 0 function, right? So let's say, let us define like another function, right? So b of x, for whatever x you put in, you get out 1, right? So we call this, I mean, not so creatively, constant 1, because you always get a 1, right? You also have c of x, right? That for whatever x you put in, let's say you put in 0, right? You get out that value. So you get 0, 1, right? And that is called the identity function. And finally, you have d of x. And what it does is that it flips your input, right? So 0. Or, okay, let me just write something else in here so it makes it clear for you guys. So a of x, it's constant 0. So it's defined at a of x equals 0, right? It's a constant. And b of x is constant 1. So it's b of x equals 1. And c of x equals identity. So we have c of x equals x, right? And finally, d of x being the, oh, should have said it, negation. Also called the not function, right? So d of x is equals to not of x. And this bar here is not, yeah? So as you can see that this is a classical function, right? And there is a 1-bit input and 1-bit output. But you can see the case of these constant functions here, right? Let me make that in green. Constant function. These constant function here, we have a problem when we try to put it in a quantum function. when we try to turn these into quantum functions, because it doesn't satisfy reversibility, right? Everything satisfies this thing, right? But it doesn't satisfy reversibility. And the reason for that is that, let's say you're applying the function a of x, right? And you put in 0, right? Let's say I tell you that you're applying the function a of x, and I tell you the output is 0. You don't know whether the input is 0 or 1. And same situation with b of x here. Let's say you're applying b of x to your input, and I tell you the output is 1. You don't know whether your input is 0 or 1, right? So that's why it's not reversible, because you can't tell from the output what your input is. And the way we can make this reversible is through this architecture here of a 2-qubit oracle, right? So let's do it again, right? So you have x here passed in, right? You have u of x and you have y here. Let's just define y as 0 here, right? You get x out and y f of x out. So this is our oracle, right? So let's say, does anyone want to choose like a function? Which function would you like me to do? A of x or b of x? Which function? Just write in chat, which one would you like me to implement? All right, okay. I'll do A, guys. The target cat is for reversibility, and I'll show you why that's important in a second. Right, okay, so let's do A of x, right? Let's say f of x, right, is equals to A of x, right? So when we passed in x here, right? Let's see, so let x equals 0, right? So we passed in 0, 0, and what we get out. So the input is 0, 0. What do we get out? We get out. Hang on, this should be 1, or should it be 0? Wait, let me try something. Okay, so it could be 0 or 1. Doesn't matter. Okay, let it be 0, guys. Okay, so and also the notation I'm using. So this is qubit 0 and this is qubit 1, right? And the way I'm writing it is like this. Okay, so qubit 0 goes first and qubit 1, right? So this is our input. You get 0, 0 in. If x equals 0, you got 0, 0 in. And the top would be 0, right? And the bottom would be, what would the bottom be? The bottom would be y is equals to 0, f of x is equals to a of x equals to 0. So 0 XOR 0 is 0. Okay, so you would get 0, 0. Right, so, and then let x equals 1, right? You would get 1, 0 as the input, and the output would be 1 because you get x here, and then you get 0 at the bottom, I think, right? Wait, so 0 tensor, wait, XOR 0. Oh yeah, you get 0 at the bottom, right? So if you look at this example here, you have 2 unique output for your input, right? So if I tell you that the function you're applying, a of x, is 0, right? And then I tell you the output is 0, 0, you can tell the input is 0, 0. And if I tell you the output is 1, 0, you can tell that the input is 1, 0. And that's what I mean by reversible, right? And that's the purpose for this thing here, is to add another space to allow for more representation in your output, right? And that makes the input and the output has the same size, and it's also reversible. Yeah. So we are going to motivate, actually, we are gonna solve a problem, right? So the problem that we're gonna solve today. Wait, so far, does anyone have any questions on this first before we go to the problem? On this page, like anything on like what I did so far?
On Zoom, there doesn't seem to be anything. I'll check Discord right now.
Yep.
Q&A. Nope. Seems like everyone's comfortable.
Oh, sweet. Okay. So we are going to our problem. So what problem are we solving today? We are solving a problem that's called constant versus balance, right? Okay, so I forgot to mention something, guys. This function right here, identity and negation, these are actually called balance function, right? Balance, oh my God, I don't have space. Balance, and the reason for that is that if you look at the output space, you can see that there are an equal number of 0 and 1, or balance, a balanced number of zeros and ones, right? And that's why they're called balance function. So given, so the problem statement, right? Given a unary function, and again, a classical unary function, a classical unary function, yeah. Determine whether it's constant or balanced, right? Okay, so let me draw you an example here, right? So let's say you have an input x, right? And you pass it into f here, and you get out f of x, right? You want to, your job is to pass in x, and by looking at the output y, tell that whether f is constant or balanced, right? And so let's say in the classical way, the way you do it is this, right? Let's say you pass in like a random input. Let's say you pass in 0, right? And you get an output of 0, right? So what function might this be, right? If you look here, right, if you put in 0 and you get out 0, we get two cases here. You get, let me delete this first. If you pass in 0 and you get out 0, you get this case and this case. So your function could either be the constant 0 or the identity function. You don't know which one is which, right? So you don't know. It's like you either get this or this. So this is constant 0, this identity, yeah. So what you would need to do is you would need to pass in a 1, right? So you pass in a 1 and you get out a 1. And now it's clear that by looking at this, you can tell that it's an identity function, right? But you would need two passes, right? So let's do one more example. Let's say now I pass in 1 first, right, into this function. Yeah, and I get out, let's say, a 0, right? So again, if I passed in a 1 here and I get out a 0, so it might be this situation with the constant 0, or it might be this situation with negation, yeah? So you don't know which one is which. So it's either constant 0 or negation. You don't know which one is which. So you would have to pass in 0 again, right? So let's say if you passed in 0 now and you get out 0. Now, by looking at this, right, it's obviously it's constant 0, right? But again, you need two passes, right? So for a classical problem, right, this is like a really simple problem, but to do it, right, you would need to pass in two inputs to determine whether your function is constant or balanced, right? And this is in the classical world. But my claim to you now would be that in quantum, right, in the quantum world, we can do this. Does anyone want to have a guess? In one pass, right? You can only you only need to pass in one number, and then you can tell whether your function is constant or balanced, right? So what claim? How are we going to do this? Okay, so let me just get something clear first. The way we're going to do this is with Deutsch Oracle, but we are not gonna look at the algorithms. We're gonna derive it ourselves, right? Just like how Deutsch gonna do it back in the days. So just let me get some facts out, some important facts. So something it's called, let's say the first thing you guys need to know is the XOR identity. So let's say 0 XOR A equals to A, yeah? And 1 XOR A is equals to not A. Remember the bar is not, guys. And you also have the X basis vectors. And this would be applying a Hadamard on 0, right? And the way I'm gonna write this is with a plus here. And that means just the upstate of the X basis vector, which is basically just gonna be equal to this plus this, right? And H of 1, oops, is equals to minus, right? Because plus and minus, and you get 1 over square root of 2 of 0 minus 1 over square root of 2 of 1, right? So easy stuff, easy peasy stuff. Then also you should remember the oracle action, right? Let's say, so you got U of F applied on the state X and Y. So I'm talking about this situation here, right? So U of F applied on the state X tensor Y is gonna be equals to X tensor Y XOR F of X. Right, so we have this in mind. Okay, so now let's go through some examples, right? Just work through some examples with different values, right? So let's say Y. Let's say we fix Y, right? Fix Y to a value, right? And let's say Y is equals to 0. Let's say Y is equals to 0, right? So you have to state U of F apply on X and 0. What would this give? Let me just copy this here so it's easy for everyone to do. So U of F, so you put X in, you got X out, so you get X here, and that is tensor with 0 and XOR F of X, right? So that's what you get out. But again, 0 XOR anything is just that thing, right? So we can write this as this. Yep, so that's what happened when Y is equal to 0. So let's say what happened if Y equals to 1, right? So U of F of X, because we don't know what X is, X could be anything, right? Of 1, and that gives us 1 XOR F of X. You guys can try to work this out by yourself. It's not that hard. It's just like a lot of writing. So you got X and you get F of X and you not that, and that's a symbol for not. So this is what you get if you put Y equals 1, right? So now let's try something. Let's go quantum here, right? Let's say Y is equals to minus, and remember the minus state is this state here, right? So okay, this is gonna be long, guys. U of F applied on X, right? And the minus state is equal to what? U of F applied to the X state. And then you have 1 over square root of 0 minus 1, right? And then by linearity, which is a fundamental property of linear algebra, which says that you can distribute matrix multiplications, because that's what UF is. It's a matrix, right? You can do 1 over square root of 2 of UF of X of 0 minus 1 over square root of 2 UF X of 1. But remember these things, guys, we just did it up here. Right? So we can just take these things and substitute them in. So finally, what we get is equals to 1 over square root of 2 of X, F of X, and that's not, minus 1 over square root of 2 UF X. There should not be a not there. There should be a not here. Okay, so we have this situation, right? So let me copy this down to another page. Right, so wait, U of F X minus, so it's equal to, oops, it's equal to this, right? So let's make some observation here. Okay, so observation 1, right? If f of x equals to 0, we have the case if f of x equals to 0, right? So we just substitute zeros into here and here, right? So what we get is that uf of x in the minus state is going to be equals to 1 over square root of 2 of x and 0 minus 1 over square root of 2 of x of 1, right? And we can make another observation here. If f of x is equal to 1, equals to 1. So again, we substitute f of x, we substitute 1 into f of x in here and here. So this, you get uf of x negative 1 equals 1 over square root of 2 x. And since we have 1 here, we substitute 1 in here. 2x and 0, right? So let's combine these results, right? You see that the top one is equals to minus of the bottom one, right? If you take the negative of this, right, you put negative here, right, and you flip that to that, and this becomes plus, so that becomes that, right? So we can make an observation, right? So for an arbitrary f of x, right, uf acting on x and minus is going to be equals to, it's going to be equals to negative 1 of x of 1 over square root of 2 x acting on 0 minus 1 over square root of 2 of x acting on 1, right? And so let's just check if this is correct or not, okay? So let's say f of x equals to 0, right? So negative 1 to the 0, that's just 1, right? So you get this, you get 0 minus 1, so that's correct. Should delete these things here so it's not that confusing. And if f of x equals 1, you get negative 1 to the 1, that's minus 1. And if you just minus this thing, you get this thing. So we're good here, right? Also, you can note out something here. We can actually factor out. We can actually factor out this x here, right? We can factor that out and factor out that out in front, yeah. And we would get inside is 1 over square root of 2 of 0 minus 1 over square root of 2, 1. But this looks familiar. This looks like the negative state, the down state of the x basis, right? So you get negative 1 f of x, you got x here, and you got a minus state here. So that was interesting. You put in x minus here, and you get a negative 1 f of x, x, and negative 1 here, right? So you get a function in terms of a phase, right? You get a function, you encode your function, encode f of x into a phase, right? And so this is what we called a phase kickback. It's one of these quantum phenomena that happens, that doesn't happen in the classical world because obviously there's no phase, right? So we have phase kickback here. That was interesting. But now let's try, here we did y, right? But now let's try with x, right? Fix x, right? So let's say x equals to 0, right? Oh, and actually let y equals to negative 1, to the negative ket. So you got the situation of uf of 0 minus, and that will be equals to, let me write this again actually. So, because that's kind of important. So u of f acting on x and minus would be equals to negative 1 times f of x. You get x here and you get minus here. Okay. First of all, does anyone have any questions so far with this page? Anything?
There is nothing in the Zoom chat and neither on Discord, so I think we're fine.
Okay, that's cool. Let me get some water first. Okay, so we get this here, right? We know the state here, and we're just gonna do this here, right? So if x equals 0, you get UF of 0 and minus state. Well, that's just gonna be equals to -1 f of 0 and 1. So literally what we did here is we substitute 0 into here, and here, right? So 3 places, right? So same thing for x equals 1, right? So you get UF acting on 1 and minus states, and you get -1 of f of 1, right? Because you substitute x in here. You get that state, right? So let's try something quantum here. Let's try x equals plus. And recall that the plus state is the up state of the x basis vector. So it's this. It's this thing here. Yeah. So let me write that down. We want u of f acting on plus and a minus state, and that will be equals to, what would that be equal to? That will be 1 over square root 2 of UF acting on 0 and 1 plus 1 over square root 2 UF acting on 1 and a minus state, right? But again, we already did these two things up here and here. So we just substitute that in, right? So easy working out in here. 1 over square root 2, and we get, actually, let me, -1 f of 0 over square root 2, just make the notation a little bit shorter. You get 0 and a negative phase plus -1 over f of to the power of f of 1 over square root 2 of 1 and minus, right? And so if you look at this, again, you can factor out, you can factor out a ton of stuff, right? You can factor out the negative state. So you get -1 to the f of 0 over square root 2 plus -1 to the f of 1 over square root 2. Shoot, I forgot the cat. 0 and 1. Put that in big brackets and here. Okay. So we get this state here, right? Because I just factor out the -1. And does anyone have any questions about the derivation of this page? Oh, there's one question. So if we act use again before, we will get the state before phase kick. So, okay, so the question is, if we act with U again, we will get the state before phase kickback. So you're asking, what if you applied U on this, right? So let's say, okay, so let's create a new page. We can do that. We have a lot of pages here, guys. The memory is so good. So so let's say U of f. So the first iteration, right? You apply an x and minus states, and you get out -1 of f of x and x and -1 here, right? So let's say so your question is, what if you apply u of f to this state, right? So let's say u of f applied to x -1, and you put a -1 f of x here, because you can do that, right? You can do that. So this is going to be equal to -1 f of x times -1 f of x of this, that, and that's going to be equals to, what's f of x plus f of x? That's 2f of x, right? So you get -1 of 2f of x, right, of x and minus. But from algebra, I think it's algebra. So it's like a to the bc is equals to a to the b to the c, right? So you can do -1 to f of x to the power of 2, right? But like -1, any power of -1 square. Actually, wait, that's stupid. Why did I do that? You can do this. -1 square to the power of f of x, -1, right? So -1 square is 1, and 1 to the power of f of x is just 1. So yeah, you get equals to x and negative. I just want to work that out, like the entire thing. No, it would would only work if y is negative, the negative ket, because if you do the plus ket, you won't get this phase kickback. So here, if we do the plus ket, how do I do it? Oh, okay. Let's add a page here. Oops, that's not what I want. Okay, so if we have a plus ket, we would, let me just copy all of this to here. Actually, let me just copy all of this. Oh. Right, if you want a plus ket, right? So just change all these to plus, right? And then you want a general case. So u of f of x plus would be just this thing, because there's no difference between this state and this state. You just get the same state out, right? So you can't distinguish between the two of them, like whether f of x equals 1, f of x equals 0, because your circuit literally has no effect on it, right? So that's why we have to has no effect, based on f of x, right? So when you use a plus ket here, you don't get the effect of phase kickback anymore. So that's why we have to use the minus ket. So yeah, that's the reason why we use it. Any other question on that thing or this thing or this? We all good? Okay, so in that case, I will continue. So, okay, we have the state here. Let me copy that to another page. So recall that u of f of plus minus, that's equal to this big thing right here. Okay. So, and also, let me copy these things down here. Okay, remember that f of x is a unary function. Recall that. That f of x is a unary function. Right, so f takes in 1 bit and spit out 1 bit. Right, it's a unary function. So we have 4 unary functions here. The first is constant 0. The first is constant 0. I'm just going to write it like that, right? That's the first, and that's defined as of f of x equals 0, right? And then the second is constant 1, and that's f of x equals to 1. Next one is identity, and that's just f of x equals to x, and then there's also negation. Let's write that as x. because in a lot of ways, the action it performs is very similar to the quantum knot. So f of x equals to not x, right? So I have these 4 cases here. So let's look at our function here, okay? Let's look at our function here. Let's say that f of x is constant 0, right? So f of x is constant 0. Then if f of x equals 0, then u of f of plus and minus would be, so okay, so f of 0 is going to be 0, and f of 0 is going to be 0, and f of 1 is going to be 0, right? And -1 to the 0 is 1, right? So we would get 1 over square root 2 of cat 1 plus 1 over square root 2 of cat 1, that. And that would be equals to, what is this? This is the plus cat, right? And the minus cat, right? So you see this here. So if f of x equals 0, you get the plus cat, the minus cat when you put that into an oracle, right? So and f of x, if f of x equals to 1, put that down here a little bit so you have more space. I think. Oh, nice. So recall again that we might have to do this a few times. Plus minus, yep, equals to this, right? If f of x equals to 1, this thing just goes to 1, and this thing just goes to 1, right? So you get negative and -1 here, -1 here. But since you have 2 negatives, you can factor out a negative face, right? So uf plus minus is going to be equals to minus 1 over square root of 2 of the 0's cat, 1 over square root of 2 of the plus cat, and you multiply that, you tensor that by the negative cat. But remember, this thing is just the plus cat, so you get negative, and this is -1, guys. It's not a it's not a cat. It's just it's something called a global face. Right? You got a global face out here, right? So if f of x equals 1, you get the situation, right? And then we have we get this done. Now let's get to I, right? And I is the identity function. So if f of x equals to x, right? So uf plus and minus would be equals to, let's see what would this be equals to. Oops. This would be equals to 0 and 1, right? So -1 to the 0, that gives you 1. -1 to the 1, that gives you negative. So -1. So that would give us 1 over square root 2 of 0 cat minus, and because there's a minus here, right? So minus 1 over square root 2 of 1, and that's all tensor by negative. So remember this thing, that's the negative cat. So what you have out is negative cat, negative cat. So that's cool. You put plus cat and negative cat into the oracle and you get negative cat, negative cat. That's nice. And the last situation we want to consider, copy that here, space. The last situation we want to consider is when the function we are trying to implement f of x is negation. So f of x is not x, right? So if f of x equals to not x, right, then f of 0 will be equals to 1, and f of 1 will be equal to 0, right? So -1 to the 1 is -1, and -1 to the 0 is 1, right? But there's a negative here and there's a plus here. If you factor out a -1 at the beginning, right, you would get 1 over square root of 2 of 0. This is 2 here, guys. Oh boy. Minus 1 over square root of 2 of the 1 cat, right? that gives you minus here. And altogether, this is negative of the negative ket tensor to negative ket. Oops. And again, this thing, it's a global phase. And what a global phase is something that it's a phase, but we can't detect it. Like we can't measure it, or we can't do anything to make it observable. So a global phase, right? So far, right? Let's bring everything together. So let's say, it's gonna write this from memory, but you have a plus minus is equals to plus minus, right? So here, right, so if f of x equals 0, you get this situation. If f of x equals 1, you get negative plus minus. Okay. Uf of plus minus equals negative plus minus, right? And then you get identity, f of x equals x, you get minus minus, f of x equals minus minus. Then you would get, plus minus minus. And the last thing I think is if f equals not x, you get negative. Yep, you get uf of plus minus equals negative minus minus. Okay, so let's just look at the output of what we have here, right? So these two are constant function, right? And what that means is that whatever value of x you put in, you get out the same value. It's constant, right? And these things are called balance because you get the same amount of 0 to 1 in the output, right? So for our constant function, the oracle gives out plus and plus, right? And for a balance function, the oracle gives out minus and minus, right? So we could clearly see that there are a difference here. You can clearly see that there's a difference here, right? That, right, when it's constant, you get plus. When it's balanced, you get minus, right? And how do we transform this into something that we can measure, right? Well, we can apply a Hadamard to it, right? If we apply a Hadamard to plus, right, we would get 0, right? And if we apply a Hadamard to negative, we would get 1, right? So far, is there any question on this before I get into like the big circuit? Yep. So we did use the same number of bits per se in the quantum case as the classical case, but what I'm counting here is how many times you use the oracle, right? So that's what I'm comparing, the classical and the quantum cases here, right? So I'm not comparing the number of bits they use, right? I'm comparing how many paths of the function they use, right? So in the classical state, you have to use two paths of the function, whereas in the quantum case, you only have to use one path, right? And so if you just use one path, and you can look at the output, whether it's 0 or 1, and you could determine whether it's balanced or constant in just one path, right? So that's what I'm comparing, and that's where like the speed up in this problem comes from. It's a number of paths, and it's not the number of qubit you use per se. Because if you think about it, right, if you, let's say I give you 2 classical bits, right, you get 0, 1, and 1 here, right? But then the function is set up in the way that there's only one function, there's only one f. Like, how do you put a 2 input into a 1 bit? It doesn't make any sense. So you got to use it twice, right? You're forced to use it twice. So yeah. Any other question? Is there any question on?
There's nothing more on Discord, so
Okay, sweet. Okay, so let me just copy this whole thing here because it's important. It's very important. That's what we get. Okay. So, okay, so let's build out circuit, right? Let's say this is the Deutsch algorithm. What do we just described here? It's a Deutsch algorithm circuit. And this is what it looks like, right? You passed in 0 here. This is the, again, this target bit. Oh, shoot, it's called the input bit, Never mind what I just said, guys. Target bit, input bit, and that's 0, right? And the target bit is 1, right? And you start with 2 Hadamard's here, right? You put it in an oracle, and you put another Hadamard here, and you measure it, right? You measure this thing, right? And I mean, the bottom one, you can measure it, but like most people just said, you ignore the bottom bit. Like you don't do anything with it, right? That's fine. It doesn't affect this measurement because as you can see here, the states, they're separable, right? You can write them as tensor products. So you can measure them separately without like you don't care about what the other one is, right? So this is our circuit. Let's try to work through this using circuit notation. Okay, actually we can do this here. Okay, so at the beginning, this is point A, B, C, D, F, G, O, point O. This is point P, this is Q, and this is R, right? So let's say at O, what do we have? We have 0, 1, like simple stuff, right? Actually, let me write them as this thing. Here we have this thing, right? At P, we get plus and minus because when you pass 0 into H, you get a plus, and you put 1 into H, you get a minus, right? So you get plus, minus, right? You get that out, and then at Q, you get UF acting on plus and minus, right? So that's, we just define it here, guys. We just define it. This is what it is. Let me delete this. And this is what the entire state vector is. This is what it looks like. You get this state here, right? And depending on the output, right, you get these 4 cases here. But in all of those cases, the top bit is in a Hadamard state. So you gotta apply a Hadamard gate to it to return the output. So that's the reason for this Hadamard here, right? So all in all, if you measure a 0, right, you get you know that your function is constant. And if you measure let's say a 1, right, you know your function is bound, right? So, and that is a Deutsch oracle, right? You just do that. And the way I would explain this is that the Deutsch oracle uses 2 techniques. The first is called quantum parallelism. And what it means is it's talking about this Hadamard, right? It creates a superposition state, right? So it's processing both states 0 and 1 at the same time, right? It's at the same time. Like people don't like me saying that, but it's what it's doing, right? It's processing 0 and 1 at the same time as a superposition, right? And the way you distinguish the 2 different output from each other is using something called a phase kickback. And that's something we talk about way back in I think, let me keep scrolling here. Let me that appears here, right? You get an f of x here. So the function itself pops up as a phase. So it encodes the oracle. What it does is encodes f of x into a phase, right? So that is what phase kickback is. So it uses these 2 techniques to determine whether our function implemented as an oracle u of f is constant or bound. So that's the Deutsch oracle for you. Does anyone have any question with the circuit at this stage?
There's nothing on Zoom, neither on Discord. So, well, there's one. Can you explain at R?
Oh, can I explain at R?
Yeah.
Yes, I can explain R. Okay. So at Q, right, you would have, let's see, let me just copy this. Oops, I think that's gonna work, right? Oops, okay. Okay, so at Q, right, at Q, depending on what your function is, right? Depending on your function is, you would have one of these four situations right here. Obviously, you don't know which one you're in, right? So let's say which one would you like to be? Like, what function would you like to apply? Just write down in chat. Like constant 0, constant 1, identity, or x. 1. Okay, let's do 1 or 0. 1 or 0, guys. We need a tie break here. We do 1 or 0. Okay. Oh, 1. Okay, there we go. We have it. We have a winner. Let's do 1. Right. Let's say we have let's say f of x. If f of x equals to 1, right? We would have this state here. So u of f plus minus equals to negative or plus minus here, right? You have this state, right? So remember, we're applying a Hadamard gate. So we are applying a Hadamard gate. So that's Hadamard tensor I. And we're applying an identity gate on the bottom, which means that we don't do anything but like to write it in terms of rigorous mathematics. You said you applying a H tensor I here, right? On this state, plus and minus. Actually, let me put the minus bottom. So this is a global phase, and you can see why, because it's not affecting anything, any calculation, because you can always put it like at the end, right? So okay, so H equals I, and this is equals to negative of H applying on this one, and tensor I applying on minus, right? So do you know what H of applying on plus state is, or do you want me to derive it? I can do it. Let's do it real quick. So H applying on, let's do it up here. So let's say sidebar. Right, so H on this one is equals to 1 over square root 2 of H of 1 over square root 2 of 0 plus square root 2, oops, 2 of 1, right? So you get the state. And then you are applying H to them individually. Oops, I think we're gonna need more space than this. Plus 1 over square root 2 of H of 1, right? So, oops, what should I do here? Oh, should paste it down here. Let's do it in another page. So I need so much space for this. Okay, so we have the state here, right? So what's H of 0? So equals 1 over square root 2 of H of 0 is just plus 1 over square root 2 of minus. And that's equals to 1 over square root of 2 of 1 over square root 2 of 0 plus 1, right? Plus 1 over square root 2 of 1 over square root 2 of 0 minus 1, right? So this is equals to 1/2 of plus 0 plus 1/2 of 1 plus 1/2 of 0 plus minus 1/2 of 1. Okay, so you can see that this thing and this thing cancels, right? Because plus and minus, that cancels. And what you have left is 1/2 of 0 plus 1/2 of 0. So that's just 1, 0. So that's just 0, right? So H of plus is equals to 0, right? So that's where I'm coming from. So h of plus equals to 0. So you get minus of 0. Tensor I applying on the minus state. So I doesn't do anything to anything, you know. So you just get minus here, right? And when you do the measurement, because they are separable states, you can just measure the first qubit, right? You measure the first qubit, right? What happened if you measure the first qubit? You get 0, right? And if you get 0, you can tell that it's a constant function, right? So same situation here. If you choose, let's say you didn't choose constant 1, you choose constant 0, right? The only difference here is we wouldn't have these global phase, right? But when you measure it, you would still get 0, right? And if you try it for identity and x, right, you would find that instead of h on the plus state, you got to get h on the minus state, and h on the minus state is going to be, I claim it's going to be 1, but you can follow the same process and derive for yourself that this thing is going to be equals to 1 and not 0 for this state, right? So this would end up in 1 minus, if you use these, if it's balanced, right? And when you measure it, you would get 1. And if you get 1, you get balance. If you get 0, you get constant. And that's the reason for this here. Does that make sense? Nice. Okay. I think the last thing we could do is we could find out what these oracles, how to build these oracles in terms of quantum gates, right? So let's just do it like super quick. Okay, so let's say constant 0. Say constant 0 is this thing, right? And that's f of x equals to 0, right? So we would have, this is the x, y, and this is the oracle. You guys remember how it's set up? Y f of x, right? What is y o plus f of x, right? And but f of x is 0, so y XOR 0 is just y, right? So what gates would create a circuit like this? What gates would you guys apply like here? Would create the circuit like this? Like just put the answer in the chat box. Wait, okay, what's the thing in the top one? Okay, it's both identity, right? So it's kind of obvious. Just identity here and identity, and you would get this situation, right? So now let's do 1, right? So f of x is equals to 1, right? So you got x up here. Let me just copy this. Oops. Okay. So you got y o plus f of x here, right? But this is just one, but anything XOR 1 is just not of that. So let's say, let me write this as here, right? Okay. So scrap that. You get not of 1. Okay, so now what gate to put in here, like top and bottom, right top first, bottom down second, that would give me the circuit. Just write in the chat, guys. Yep, x, wait, I and x, very good. So easy stuff, right? And now we have I, which is f of x equals to x, and that's y. Oh God, should have copied it. And y, this is y x or f of x, but f of x equals to x here, so y x or x, right? So this is a little bit more difficult. So I'm going to give you guys a hint and say that it's a 2-qubit gate here. Okay, that gets out x and y, O plus x. So what gate would I put in here that would result in this action? Does anyone have any idea? So did I ever define? Yeah, really good. C naught. Did I ever define what C naught does? I don't think I did. Did I? Nope, never did. Oh, shoot. Does anyone remember which notebook it comes from? Not this one. Oh, there we go. Oh yeah, no, okay. So I never defined what a C naught is, but really good, guys. It's a C naught, right? So let's test some values in here, right? So let's say x is 0, right? And y is 0. So x equals 0, y equals 0. We get 0 here, and 0 XOR 0 is 0, right? So x becomes y tensor y XOR x, right? So x equals 1, y equals 1. So you get 0. Wait, shoot, should be 0 here. Okay, so x equals 1, right? You could get 1 on top, and then 1 XOR 0 would be 1, right? So that's what identity does. So it looks correct so far. Let's try x equals 1, y. X equals 0, y equals 1, right? So you get 0 up here, and you get 1 here. But so you might think it's flipped, but it's not, because it's just this thing. You get 1 XOR 0, and that's just 1, right? So because y is different, that's why you flipped it. Oh, I'm seeing answers in the chat that says I and C naught. C naught is a 2-qubit gate, so you only need like one thing. You don't need I for anything. You just apply C naught, and that acts on 2 gates. So you would do C naught, that would act on x and y. And so the exercise for today is for you guys to find the circuit for f of x equals not of x. So this x, and here it will be y o plus not of x, right? So it's a little bit more difficult, but I think you guys can do it. So and hint there, but let me give you guys a hint. Really nice, dude. Like, some people in the chat already got it, so if you just want to like have a peek in the chat, you guys will have no problem with the homework. So it will look something like this. This is probably too much hint for you guys, but hey, not many people attend this lecture, so might as well give out some freebies, Not x, right? So I mean, there's only one gate here, so I'm gonna just give it to you guys. It's C next, and then yeah, that's right. You can't express them as separate bits. No. You can still do it unless you have a Hadamard before that. Like normally, if you just get 0, 1, right? You apply a CX here, right? That just gives you 0 and 0, and you can still do that as tensor products. It only happens if you pass in a superposition state, and that's where the entanglement happens. And that's where, like, that's the infamous entanglement circuit is distinct, right? The powers in these two things, you need to have both components for the entanglement thing to happen. So yeah, so this is homework for you guys, right? Homework. And besides that, I think I'm done. Does anyone have any question with the circuit building these 2 pages? Not this. I can't answer that. That's homework, But like these 3 here. Does anyone have any question? Emilio, are we all good? if we don't have anything in Discord, I think yep, I'm done.
Yes, it seems like we're all good. I checked both Discord and chat. So yeah, thanks everyone for coming. Thanks Minh for explaining Deutsch's algorithm beautifully. And I just wanted to tell you guys, for those of you who are doing the clinics, they start in like, it depends what group you're in, but they start in like, the first one starts in around 30 minutes. So I'm in touch currently with the first sort of speaker. And yeah, we're setting up the Zoom and everything right now. So just everyone just talk in the groups, try to mingle, try to meet each other, just so we can have some I don't know, uniformity as to what we're gonna talk to them about, you know, just so it can be clear. So
Wait,
that'll be good if
what's-
we. Sorry.
What time's the talk again?
It's I think 7 p.m. IST is the first one. Oh, Prasad has a question. It's what's the application to Deutsch's algorithm? Go ahead.
Yeah. So Deutsch algorithm doesn't have any application. Let me just tell you that, right? But it gives inspiration for something called the Deutsch algorithm, which is the generalized Deutsch, right, for n qubit, right? So now you guys are just working with unary function, which means that there are only one input. But what if you want like 10,000 inputs, right? Then Deutsch has something. Let me write down the name. Is this correct?
Yeah.
Right. This function, right? It creates a circuit, and it can tell if a function or is constant or balanced for like a function with like an arbitrary number of inputs, right? It can do that. And if you look for the proof on how to do it on a classical computer, you can't do it very efficiently. So that's like the first example of like real quantum speed up, you know, like there's like some technicalities to this because, you know, you use 2 qubits instead of 1, but like you use 1 pass. So there's like some technicalities, but like in that there's like real examples. And then for like another algorithm that uses the exact same circuit as Deutsch is something called Bernstein-Vaterani. And that's like one of my favorite algorithms. And then Shor's also takes inspiration from these things because it's like the most basic kind of thing you can do with a quantum circuit, you know, to provide speed up. And it always come back to phase kickback, entanglement, and superposition. It's always those two, those three.